Yeah, good evening. So please type in the chat box. Is the audio and video fine? So welcome back to this session, guys. So please type in the chat box. Is the audio and video clear to all of you? Yes. So just confirm the audio once and the video, of course. Hi, good evening, all of you. Yeah, clear? Okay, good. So welcome back to this sessions basically on engineering mathematics that are happening at 7 p.m. So basically, if you see, this is lecture number 5 of linear algebra. So we have started linear algebra as the first module, and we were actually at lecture number 5. Okay, and the prime focus in today's lecture would be system of equations. You know, because in the last lecture we were talking about rank of a matrix, okay, determinants, and we have extended to the concept of a rank, and we have seen row echelon forms and what we can different properties of ranks of a matrix. Okay, so we'll see. I actually want to talk about nullity as well, but I think it would be better if I talk it about after teaching you vector spaces. Okay, so we'll teach nullity and all in the upcoming lecture, that is in the next lecture. But in today's lecture, the prime focus would be system of equations and also eigenvalues and eigenvectors. Okay, so I think time for diagonalization might not be sufficient, but we will look at the system of equations. What are different system of equations that we can generate, like in terms of solutions, and then we can look at eigenvalues and also eigenvectors. Okay, so what is an eigenvalue, and at the same time what is an eigenvector, or how you will actually calculate eigenvalues or basically eigenvectors of a matrix. Okay, so these things we are going to look here. And if you basically see, this is Telegram channel for the Wallah English YouTube channel, of course, and if any update on this channel is being posted in this Telegram channel, so you can scan this code. It directly enables you into the Telegram channel of Wallah English. Okay, so any lecture or any update on this channel will be posted here, so you can be in touch. And this is my personal group, Vinaysa PW. Like, you can just join this if you feel I could help you at some point. Okay, and this group is maintained by me and my students, of course. So here any lectures or anything that's going to be taken by me will be posted here. And not only that, it's also it's also talks about a lot of notifications from other faculties and other complete team of PW actually. Okay, so these are the two channels that you can go for. Sorry, it's not working. It's working because we have even tested today, so please scan this properly. Okay, GATE CSEs have complete subject wise courses planned only in this English channel. Yeah, basically see, first we have started with this maths, and as this course progresses, we'll come up with more updates. Okay, and now coming to this Unity PW. So this is a online platform where you can have all your track record at one particular place. Okay, so the only thing you have to do is, firstly, you can type Unity PW in the Google. So once you type Unity PW in the Google, it asks you for sign in. So you can just sign in with your normal Google account. Okay, then the only thing that you should do is, normally when you're typing in the chat box, you can have this exclamation mark and then doubt. Okay, so whenever you have this exclamation and doubt and then you type your doubt, this doubt will actually get stored in a particular place. Okay, where you have the Unity login. If you click login, this is how your page gets displayed. This is my page. Of course, you can see my name. Similarly, you can generate yours, and all your polls, all your points will get shared here. So that's definitely, it's like a one place storage of all your important points. Okay, and similarly, during notes making, if you have any issues, you can just type hash notes actually. Okay, so exclamation notes and then exclamation note. If you type, then definitely it will take you that will take your point into this space again, which is available. Clear? So I suggest you basically to better log in into this Unity and have a track record of all your doubts and notes at one particular place actually. Okay, then coming to the last lecture. So in the last lecture, we were talking about rank of a matrix exclusively. Rank of a matrix, correct? So we were talking about rank of a matrix, and we have talked about some properties. Okay, determinants we have gone in much detail, and also we have talked about properties of rank of matrices. Okay, basically, especially when multiplication is taking place. Okay, so rank of multiplication of two matrices is less than or equal to minimum of rank of A comma rank of B. So these kind of points is what we have seen, of course, in the last lecture. Okay, so I have given you homework of 2 questions actually. Did you all solve those 2 questions? So the first question is this: which one of the following does not equals this particular determinant? Okay, so if some of you have solved this question, then definitely you have answer for this. So I'm giving 30 seconds to enter the answer. So please enter the answer. Can you please provide any schedule for that, sir? Yeah, just wait, Satvik. As we progress in this course, things get revealed, and you can have better idea on what's coming up. So if you have solved this question, then please enter the answer. If you have solved this question, then please enter this answer. A, B, C, D. Okay, this is B, so please be careful. A, B, C, D. Okay, then let's see. No one typed answer in the chat box. People typed or not? Rank of AB less than or equal to this property, please clear once. Yeah, I'll tell you. Okay, so just a minute. If you see this, like we have seen, the product of two non-zero matrices can be a zero matrix. Okay, so whenever you take two non-zero matrices, which means at least one of the element in the matrix is non-zero. Okay, so the minimum possibility is this can be 1 and this can also be 1. Okay, but if you multiply this A and B, you'll get a null matrix, and the rank of a null matrix is 0. Okay, so that's how this statement can be actually validated. Normally you can prove this using initial notations and knowing some properties of rank nullity theorem, but right now I'm just giving the point for you. Clear? Okay, now let's see, coming to this question, I just want to give you one hint. Many of you might have tried different ways of solving this question, but I want to give you in one important form actually. So if you take this determinant, for example, okay, so if you take this determinant like 1, then if you multiply x square plus x plus 1 is what you have, 1, then y square plus y plus 1 and 1, z square plus z plus 1. This is what you have actually. Okay, so this is the first determinant, the determinant in the option A. Now if you want to solve, you can solve like if you apply R2 changes to R2 minus R1, R3 changes to R3 minus R1, then these two elements become zeros. You can calculate the determinant. Similarly, you can calculate the determinant of the question, which is a determinant of the matrix which is given in the question, and you can check whether determinants are coming to be equal or not. But in general, whenever there is some plus signs in the determinant, within the determinant, you can actually expand this determinant. Okay, so how you can expand, I'll show you today. So see here, this can be expanded as, see here, let's, for example, if I call this first terms as A, then this second terms as B. Similarly, in the third column, this first terms as C and this last terms as D. Okay, so here basically you have a set of two terms in each column, in each row. So the first set of terms I'm calling it as A, and the second set of terms I'm calling it B. Similarly here I'm calling the first set of terms as C and the second set of terms as D, of course. Okay, if you split this, it turns up like this, 1 1 1 anyhow. Then you can take the first step, then it's like x square y square z square, and you can take the first here also, x y z. This is what you have, plus then here you have only 1 1 1, but here instead of taking, okay, you take the first row, still x square y square z square. Here since you have already taken C, now you can take D, 1 1 1. It's like the possible combinations, that's it. Okay, then again 1 1 1, of course. Now since the combinations, both the combinations with the first terms is finished, now come to the second term, x y z x y z plus 1 1 1 x y z, and this is 1 1 1, of course. So this is how you can expand. In fact, if there are two terms here in the first column also, we would have got total 8 determinants. Okay, like this is just like the splitting up. Okay, you can see we have split it up into 4 determinants because there are 4 possible combinations which you can write like this. Okay, now when you take this, ultimately this determinant is 0. Why? Because first column and third column is same. Similarly here, this is also 0 because second column and third column is same. This determinant is also 0 because first column and third column is equal. So this total value will be just equal to this determinant, and if you check the question, it is actually a flip of this, correct? Means if you see the determinant which is given in the question is the same determinant but with second and third column interchanged. That means this determinant value will be negative of this determinant value. They both won't be equal. Yes or no? Correct? Did you understand this? If you check this determinant, and if you check the determinant which is getting balanced here, these two columns got swapped. So ultimately the value of this determinant would be negative of the actual one given in the question. Correct? Can you understand this? Yes or no? Please type in the chat box. Is this clear to all of you? Did you all get this? The determinant which is left here is actually having C2 and C3 interchanged. Okay, so that's why this will have a negative sign excess as compared to the given determinant. Clear? So which is equal to minus 1 1 1 x y z x square y square z square. That's it. Okay, so that's how you can see clearly there is a difference of a minus sign. Okay, so A is a correct answer. Then if you check B, ultimately you can observe this 1z z square, 1z z square is as usual. Now if you apply these transformations, first transformation what they applied is see R1 changes to R1 minus R2, R2 changes to R2 minus R3. If you do these transformations, then ultimately these two elements become zeros, which is here. This first term becomes x minus y and second becomes y minus z. This becomes x square minus y square and this is y square minus z square. So this matrix is obtained by R1 changes to R1 minus R2 and R2 changes to R2 minus R3. Okay, so these are the transformations which you have done in order to get this determinant. So this is not swapping. Okay, so this is our transformations clearly, and definitely by doing our transformations this determinant got converted to this, so these two will have the same value. So this cannot be the correct answer. Okay, because the value of the determinant is equal in this case. Now coming here, if you just expand this again in the form, you will again get the same determinant. Okay, because the only difference is this two gets swapped. I mean, this is what you actually get in this expansion. Like for example, if you expand this, you will see if you expand this 1 x x square, 1 y y square, 1 z z square. Okay, plus 1 1 1 x y z you retain, and since you have already used the first terms, now go for the second terms 1 1 1. Now you have written all the possible combinations by taking first terms. Now write taking the second terms 1 1 1, here also 1 1 1 because you have 1 1 1s, x square y square z square plus 1 1 1 1 1 1. Okay, and this is again 1 1 1 of course. Okay, so this is what you'll get. So clearly all these three determinants are zeros. This is 0, then this is also 0 because first column and second column are equal, first column and third column are equal. So this determinant is same as this which is given in the question again. Okay, now coming here, this value, this is obtained by R1 changes to R1 plus R2 and R2 changes to R2 plus R3. So ultimately this and this will have the same value again, so this can also be not chosen. Okay, in fact the value of these three determinants will be same as that, but the value of the first determinant will be negative sign of that, which we have actually shown here in this case. So that's why option A is the correct answer in this case. Clear to all of you? Yes, did you all understand why option A is the correct answer? The determinant of the value of this and the value of this are not equal because there is a minus sign difference between both. Clear? Because individually to expand and do the things, it takes some time. Okay, you have to expand, then again check whether the values are coming correct or not. So this issue was there, but that need not be done because of these simple expansions. Okay, this is how you can expand a determinant. Is this points clear to all of you? I know some of you might be learning it for the first time, but is this clear to each and everyone? Okay, so the correct option is of course option A. Let's see how many of you have done it. Why the poll is not activated for you in the past? Okay, fine. So this is option number 1. This is the first question. Now coming to the second question. So this is the second question I have given you. A and B are two 3×3 matrices such that A is this and B is a non-zero matrix and AB equal to 0 of course. Okay, the rank of the matrix B is dash. Okay, so let's see how many of you have solved this question. You can expand the determinants and check. Okay, because anyhow option B and option C, option C and D. Okay, C and D in this case, C and D you can easily identify. You can just have to check between these two. That's it. Okay, you can just expand the determinants and check. Fine. Okay, so if you have solved this question, we have given points actually based on some idea in the last class. A is not equal to 0 of course. Okay, some non-zero matrix, and B is also non-zero, but AB equal to 0. This implies clearly we have seen determinant of A should be 0 and determinant of B should also be 0. Correct? Now tell me one thing. B is a matrix of size 3×3. If B is of size 3×3, if B is 3 by 3, then and determinant of B is equal to 0. This implies rank of B is less than 3 actually. Yes, it could be less than or equal to 2. We don't know whether it's 2 or not 2, but we know only one thing, this rank of B is less than 3, which means it is less than or equal to 2 in fact. Okay, so anyway, if you just take it up, this r equal to 3 is wrong because determinant of B is 0. This equality sign is there here, so this is also wrong. Okay, these two are wrong. Then r equal to 2, we are not very much sure. Okay, we only know r is equal to 3, we never know whether it has a 2 by 2 minor or not. Okay, so the only thing which you can say confirmedly is rank will be less than 3. That's all you can say. You cannot assure that it's only 2, it can be 1 also. Okay, so that's why. Clear? So option B is the correct answer. We cannot assure this, so B would be the correct option in this case. Okay, poll is not working here. Poll is not working. Poll is not working. Rank of B not equal to 0. Yeah, rank of B cannot be equal to 0 because that should be a non-zero matrix. Okay, but at the same time, if you check in the generality, this is the most convincing option. Okay, it can be 1. Clear? It can be 2 or it can be 1. It's not 0, I do agree, because it's non-zero matrix. Clearly they have given B is not equal to 0. So, but it can be 2 or 1. So that's why without loss in generality, we'll take that rank is less than 3, of course. Okay, because it is clearly given it's not equal to 0. So anyhow, we know that rank is not equal to 0, of course. Okay, guys, are you not able to get the poll today? Is the poll getting displayed for you? No? Yes? Because I'm seeing no comments actually at any point. That's why. Okay, so now coming to today's class, we'll be focusing on system of linear equations and also on eigenvalues and eigenvectors, of course. So let's see. First, let us go with system of equations. Okay, system of linear equations. So clearly, system of linear equations would be something like, if you have a system, first I'll explain you with a 3 by 3. a11x plus a12y plus a13z is equal to b1. a21x plus a22y plus a23z is equal to b2. a31x plus a32y, because I'm explaining with 3 by 3 so that it would be easy for you. Then we'll extend to m by n general form. Okay, so let's say this is a linear system of equations. We have it's a clearly poll not showing now. Okay, I'll try to do something. Maybe I'll refresh and like check. So anyway, let's see here. So this is a linear system. A linear system of equations. A linear system of equations. Now, yesterday someone was asking me how I can write this system into matrix form. Okay, so just see, if I can write a matrix in such a way, a11, a12, a13, a21, a22, a23, a31, a32, a33 multiplied with x, y, z, it's a column vector. This would be equal to b1, b2, b3, of course. Correct? Yes or no? This is what I can convert. Like for example, if you multiply these matrices, okay, this is of size 3 by 3 here. I have simplified things to show you something. This is of size 3 by 1. This is also of size 3 by 1, of course. Now if you multiply these two matrices, ultimately you'll get again 3 by 1. So if two 3 by 1s are equal, corresponding element should be same. Okay, now if you multiply a11 into x plus a12 into y plus a13 into z, so in this resulting 3 by 1 matrix, the first column element would be a11x plus a12y plus a13z. Now that should be equal to b1, which is same as this first equation. Yes or no? Similarly, if you multiply this second row with this column, a21x plus a22y plus a23z, which is the same here, is equal to this second element. Similarly, by multiplying this row with this column, you will get a b3 actually. That's how this system can be brought into matrix form, and this is in general written as ax is equal to b, of course. Okay, and this a is called coefficient matrix. Coefficient matrix. Then this x is called unknown vector. unknown vector, and this b is the constants on the right hand side. So this is a constant vector. Okay, so ax is equal to b. That's how basically a system in a general linear form can be brought into a matrix form. And now there are plenty of ways to solve these systems. We'll see how we can solve and all. But before actually solving the system, like I was telling you yesterday, if I give you one system and if you try to solve that system, okay, now after some time, let's say for example you're not able to solve that system, okay, after some sequence of operations you found out you cannot actually solve that system. So this complete process what you have done for some time is wasted. So initially, before actually finding the solution, it's important first to check whether a given system will have a solution or not. Okay, we are not interested right now in the what is the solution of the system, but whether we are interested in the question whether the system has a solution or not. Okay, so that's what we call consistency checking of the system, and we will define certain rules for checking the consistency of the system. Consistent means basically the system having a solution. Inconsistent means the system do not have a solution actually here. Clear? So this is what we have. Always 3x1 matrix is a vector matrix. Yeah, basically it's called a column. This is called a column vector. Okay, that's it. Because if you are writing vectors in a 2D space or in 3D space, you write alpha, beta, gamma as the coordinates. So that can be represented in the form of a vector. Clear to all of you? Is this clear to each and everyone till here? We can form this linear system into this matrix form, of course. Okay. Now few times what happen is, let's say we have in general a m by n into x n by 1 is equal to b m by 1. This can happen. Okay, so which means here you have exactly 3 equations with 3 unknowns, but sometimes you can have number of equations and number of unknowns different actually. Okay, so m is the number of equations in general. M is number of equations and n is number of unknowns. Okay, so this is number of unknowns actually. Now let's see if you have this ax is equal to b. As I told you, this a need not be symmetric. A need not be always a square matrix. The reason for that is when you are dealing with physical systems, sometimes the number of variables could be large than the number of conditions what we have. Okay, let's say initial conditions or boundary conditions. So depending on that, sometimes we get more equations than the number of unknowns. Sometimes we don't have enough information and we have less equations than the number of unknowns. And sometimes number of equations, as many we have number of unknowns, the same we have number of equations also here. Sorry, Satya, where can I find the notes? App also I'm unable to see the notes. No, you can see actually if you click on the link where it's directing, if you click on that, there is something called free batch. So in free batch GATE 2025 preparation in English, you can get the notes. Okay, now let's see how to actually check whether this system has a solution or not. Okay, so for that, first of all I'll talk about 2 by 2s. Okay, I'll take 2 equations with 2 unknowns. I'll explain you. The same can be extended generally for this system. Is this clear to all of you till this point? Everyone who here is on live, so all of you please type in the chat box. Is this clear to each and everyone what we are going to do? Okay, so first we have converted this linear system into matrix form, and now our point of interest is to check whether this system has a solution or not. Okay, how we'll check that and all we'll see now. Okay, fine. Now let's see checking consistency means availability of a solution. Availability of let's say availability of solution for a given linear system. Okay, so now you have got a linear system. So let's see how to check whether it has consistent or not. So before going for this formulas, possibilities and all, we will check case by case. Okay, so case 1. Okay, or let's say, yeah, okay, example. I just want to look with one example first. Let's say you're solving 2 equations. Let's say x plus y equal to 5 and x minus y is equal to 2, for example. Okay, so x minus y is equal to 1, let's take. Okay, so 1, so that it's easy. So now you can see this is like of the form 1 1 1 minus 1, or let's say 2x plus 3y is equal to 10. Okay, so 8, let's say 8, then x minus 4y is equal to minus 7. Okay, so let's say you take this system, for example. Now when you take this system, one thing that you can find is these are linear equations, you can plot them. So if you plot, you can plot in Desmos also, but I'm just showing this. So see here, you know how to plot a straight line. If I give you the equation, so this is x-axis and this is y-axis, of course. Now if you plot this line, if you take the x coordinate, okay, if you put y equal to 0, x equal to 4, so x equal to 4, of course, so x equal to 4 is here, 4 comma 0. Now if you put x equal to 0, y equal to 8 by 3, so roughly 2.67 somewhere. Okay, so let's say somewhere here. Now let's see, we draw a straight line passing through these 2 points. So you can see there is a straight line that passes through these points, of course. Okay, so there is a straight line that passes through these points. Fine. Okay, so this is the line that you have, which is something like 2x plus 3y is equal to 8. Okay, now coming to the second line, x minus 4y equal to minus 7. So if you put y equal to 0, x equal to minus 7, so x equal to minus 7, maybe I'm not drawing as per the scale, but just to give the idea, this is minus 7 comma 0. Now if you put x equal to 0, this y equal to 7 by 4, so y equal to 7 by 4, so this is 7 by 4 is like less than this, 1 point something odd. So if you plot this, then this line could take this form. Okay, so this line could actually take this form. Now if this line is taking this form and this equation is x minus 4y is equal to minus 7, of course. Okay, now you can understand one thing, these two lines will intersect only at one particular point. Okay, so this is the point of intersection. Right now we are not bothered what is that point, what are the coordinates of that point, but you can find there is one solution to this system. Yes or no? Means these two lines will actually intersect only at one point. You can even plot the curves using Desmos. Maybe I'll show you in Desmos also. That's make the life little colorful. So see here, let's see. First equation is 2x plus 3y equal to 8. So let's say 2x plus 3y equal to 8. Okay, so oh sorry, nothing is getting typed. 2x plus 3y equal to 8. Okay, so this is the line what I have shown. So this is coordinates 4 comma 0 and this is 8 by 3, which is 2.67. and next we have x minus 4y equal to minus 7, x minus 4y equal to minus 7. Okay, so you can see this is how you got, ultimately this point will be less than this 2.67. so if you plot different points, so this is 1.75, which is 7 by 4, of course, which is less than 0.267. so that's what we have tried to replicate here, and these two will intersect at only one point. Okay, so physically these two intersecting at one point means this system will have only one solution, which is exactly at this values of x comma y. Okay, like if you want to check what are the values of x comma y, so x is 1 comma 2. Okay, so this point here is 1 comma 2, of course. Okay, so because when I'm framing these equations, I have set x equal to 1 and y equal to 2. So if you plot it, it comes up like this. Now let's see this, the above set of equations has a unique solution, it has solution, but it's only unique, it has only one solution. Okay, and more importantly, if you write this in matrix form, you would have got 2 3 1 minus 4 x y is equal to 8 minus 7. Okay, so this is the system. Okay, so if you compare this, we have a, x and b, of course. Okay, so leave it like this. Now let's see, let us go to a second example, we'll visit back. Okay, or else I'll finish the story here itself. Look, the system is 2 3 1 minus 4 x, okay, x y equal to 8 minus 7. Okay, this is what you have. Now we generate something which is called, this is A, clearly this is A and this is B, of course. Now we calculate something which is called augmented matrix. You know, augmentation means joining. Okay, now you might have heard this word in English. Augmentation means actually augmenting, so joining. So if you get for this augmented matrix, augmented matrix is nothing but A augmentation to B, means you have joined this column vector B to the actual A matrix, which gives you something like 2, 3, 1, minus 4. Then you have to add this column to here, so 8 and minus 7. This is the matrix. Now if you try to calculate the rank of this matrix, for example, okay, so this is of size 2 by 3, so maximum possible minus you can form is of order 2 by 2, and clearly you can see clearly rank of A, if you calculate this, because it's a 2 by 2 matrix, if you calculate determinant, minus 8, minus 3, minus 11, which is non-zero, so this is 2, and clearly this matrix is also one of the 2 by 2 minor of this matrix. This implies rank of A augmented B will also be equal to 2. Yes or no? Correct? Will you understand this? What I am telling you is, if you just calculate, since it's 2 by 2, I am just calculating determinant. Minus 8 minus 3 is minus 11, which is non-zero. Okay, so since this is non-zero, the rank of this matrix is 2, and since this matrix is also present as one of the 2 by 2 minors, definitely this rank of A augmented B will also be 2. Correct? Because that means the 2 by 3 matrix has at least one non-zero minor, and this is 2, 3, 1, minus 4. So therefore this rank is also 2. Is this clear to all of you? Which means these two are actually same. Yes? So please type in the chat box, is this clear? In this case, when the system has got a unique solution, these two are actually same. Rank of A and rank of A augmented B is same. Okay, now let's check one more case. Like this is example 1. Now let's go to an example 2. Example 2. Okay, so let's see what happens in this example 2. So let's take 2x plus 3y is equal to 6, 4x plus 6y is equal to 12, let's say. Okay, so these are two linear equations. Of course you can identify that second equation is 2 times of the first equation, but anyway, let's say there's only two equations like this. Okay, now if you again write it in the linear form, 2, 3, 4, 6 times x, y is equal to 6, 12. Okay, and clearly this is A, this is your x, and this is B, of course. Okay, which is the constant matrix. Now if you try to plot these two equations, what happens is, this is your x-axis, of course, and this is your y-axis, origin, x and y. Now let's see, 2x plus 3y equal to 6. If you for example put y equal to 0, x equal to 3, so this is x equal to 3 is somewhere here, and if you put x equal to 0, y equal to 2, so let's say this is somewhere here, 0 comma 2, of course. Then if you connect them with a straight line approximately like this, okay, then this is the equation of 2x plus 3y equal to 6, of course. Okay, so 2x plus 3y equal to 6. Now can anyone tell me, if I plot this second equation, what happens, or how can I see? Basically if I plot this second equation, 4x plus 6y equal to 12, that means if you put x equal to or y equal to 0, x is again 3, so the same point, and if you put x equal to 0, y equal to 2, so again 0 comma 2, this same point, which means if you try to plot the second equation, the second line will just overlap on the first line. Correct? This will just overlap on the first line, means you cannot clearly see a distinction between the two things. So when we have the matrix like m by n equal to 2 by 3, not 3 by 3, then how should we calculate the rank? I'm telling you. Okay, I'll generalize after this. Clear? So these two will be just overlapping each other. Yes or no? If you plot any one of these equations and then you try to plot the second equation will just lie on the first equation. Yes? Yes or no? Are you all getting this or not? The second equation will just lie on the first equation. Now tell me one thing, if two surfaces are in contact, okay, or if two lines are in contact, let's say for example, if you take this as a small line and if you also take this as a very thin line, and if I make a contact between these two, can anyone tell me how many point of intersections I'll have? If two lines are just lying on each other, then how many point of intersections do I have? How many point of intersections do I have? If two lines are just overlapping each other, then how many points of intersections you have? Infinite, correct? So this means it has infinitely many solutions. You take any value of x on this, on one line, x comma y on one line, definitely that will also satisfy the second equation. So you have infinite solutions. Infinite solutions actually, okay, so that's infinite solutions. So that means you can observe the plotting of both the equations, the plotting of both the equations, gives us infinite points of contact or infinite number of solutions. Okay, so this gives you infinite number of solutions. Why I have not taken 3 by 3 is, in 3D you have to plot planes, which is a bit in 3 by 3 you have to plot a, planes actually, which is a bit complicated, so that's why I'm dealing in 2D. Okay, now let's see, this gives you infinite number of solutions. Then if you now check the rank story, okay, let's see what happened. A is equal to 2, 3, 4, 6. B is equal to 6, 12. Okay, then if you check a rank of A, so first of all this is a 2 by 2. So if you check determinant 12 minus 12, it is 0. So then going for 1 by 1 minus, clearly rank of A is 1. Okay, now if you go for this A augmented B, 2, 3, 4, 6, 6, 12. Okay, then if you check the if you try to calculate the rank of this, okay, let's apply R2 changes to, because we'll make this 0 initially, R2 minus 2 R1. This yields us A augmentation B would be elementally identical to 2, 3, 6. Then after 4 minus 2 times of 2, which is 4, so this is 0. 6 minus 2 times of 3, which is 0. 12 minus 2 times of 6, which is also 0. So in this row echelon form, you have only one non-zero row. So this implies rank of A augmented B is also 1. Correct? Yes or no? So can we generalize that is for infinite solutions? The rows will always be proportional and vice versa. See, when rows are vice versa or proportional, it depends, okay, on this constant. We will see. Okay, that's what I'll show you the next. So just be patient for 1 minute. I'll show you. Rank of A is also 1. So here you can understand one thing. In this case, where you have infinitely many solutions, of course I'm making the job very easy here, to be drastic. To be honest, I have brought it very down to the complexity level. But in actual case, in order to show these conditions, rank of A equal to rank of A augmented B and all, it's like a big thing again. Okay, you have to go very deep into the ranks, which is even out of the scope of GATE syllabus. Okay, so that's why I'm just giving rank of A is equal to 1 and rank of A augmented B is equal to 1, of course. Now clearly you can understand rank of A is equal to rank of A augmented B, but this is less than 2 actually, correct? So this is less than 2. This is less than 2 in this case. This is what you can observe. This is 1, this is 1. So both are equal, but these ranks are individually not equal to 2. They are something less than 2. Okay. Now let us look at example 3, the last example, which could clear certain things for us. You take the equations, say for example x plus y equal to 5 and x plus y equal to 7. Okay, so let's take these two equations. Now clearly just by looking you can say those equations don't have solutions, because if it has solution then ultimately 5 should be equal to 7, which won't happen, of course. So you can see if you plot this, these are parallel lines actually. Okay, or you can write maybe 2x plus 2y in order to, if you want to increase some things. Okay, then let's see if you plot these equations, for example, origin x and y. So x plus y equal to 5. So if you put y equal to 0, x is 5, and x equal to 0 gives you y equal to 5. So which means if you plot a line like this, you will have this coordinates as 0, 5, 5, 0, of course, and this is x plus y is equal to 5, of course. Okay, now let's see one more thing. If you try to plot this, if you put y equal to 0, x equal to 7 by 2, 3.5, and if you put x equal to 0, y is also 3.5. So which means you can have a parallel line like this. Okay, you'll have almost a parallel line, such that you'll almost have a parallel line in such a way. This point is 3.5, 0, and this is also 0, 3.5. And clearly if you check the slopes, the slope here is -1, the slope here is also -1. That means these two lines are parallel. Okay, so this is 2x plus 2y equal to 7, and this is x plus y equal to 5, and these two are parallel lines. Okay, so you can check these two are of course parallel lines. Now if these are parallel lines, can anyone tell me, is there any point of intersection for them? What are the number of solutions these two lines or basically this system has? Can anyone tell me what are the number of equations, or basically what are the number of solutions this system has? Number of solutions that this system has? 0, right? Because both of them are parallel lines actually, and they do not provide a point of intersection, so ultimately there is no solution for them. Okay, so clearly you can see, since this has no solution, that is, the system is inconsistent. The system is inconsistent. Okay, so it don't have a solution, of course. Yeah, 2. It has 0 solutions. Now let's see, if you again check the ranks, what's happening with the ranks of the matrices. A is equal to 1, 1, 2, 2, and B is equal to 5, 7. Okay, now if you calculate rank of A, for example, rank of A is clearly 1. You can see, because it's a 2 by 2, clearly determinant is 0, so then you go for 1 by 1, so you have at least one non-zero element, so rank of A is 1 directly. Now calculating this A augmentation B, you will check rank of A augmentation B, 1, 1, 2, 2, then 5 and 7. Okay, now here if you check what is the rank of this matrix, if you want to make this 0, R2 changes to R2 minus 2 R1. This implies A augmented B is equivalent to 115, then 2 minus 2 times of 1, 0, 2 minus 2 times of 1, 0, 7 minus 2 times of 5, which is -3. So this clearly tells you rank of A augmented B is equal to 2, of course. Okay, because this is non-zero, so clearly there are 2 non-zero rows in this echelon form, so we have a rank of A augmented B is equal to 2. So one point that you can understand here is, therefore rank of A is not equal to rank of A augmented B. This is what you have observed here, correct? Yes or no? 2, because I would have taken 3 by 3 also, but in case of 3 by 3 I should plot planes. Okay, so which could make the life complicated, but in 2 by 2 you can understand simply. So I have shown here, if you have a unique solution, first thing that you found out is rank of A is equal to rank of A augmented B, and also that's equal to 2, and this 2 represents the number of elements in this vector. Okay, which is basically the number of unknowns in the system. Clear? So this 2 will be equal, and that's also equal to number of unknowns in the equation. Now if the system don't have a unique solution, it has infinitely many solutions, then these two will be still equal, but the ranks will be less than the number of unknowns actually. Okay, ultimately that's what you have, right? Whenever the equations are more and number of unknowns are less, then ultimately it's a overdeveloped system, so ultimately it can have infinitely many solutions. And coming here, these two will not be equal, okay, which you have checked here. So in general, for any system of A m by n, Ax n by 1, and B n by 1 m by 1 again, you can see in general, for the system for the system a m by n x n by 1 is equal to b m by 1, of course, if you have this system, and this b is non-zero, of course, okay, b is non-zero, that is a non-homogeneous system. Non-homogeneous system. What's a non-homogeneous system? Why it's called a non-homogeneous? You can see if you take any of this equation, the term in this, like for example, if you write that equation as x plus y minus 5 equal to 0, okay, equal to 0. Now it has three terms. This is the first term, this is the second term, and this is the third term. Of course, you put the minus n inside, no issue. Then this term has a degree is equal to 1, correct, because it's x power 1. So this term has a variable x and there is power 1 on top of x. That means this term has a variable of x and of degree 1. So this term has degree 1. Similarly, this term has also got degree 1. But if you check this third term, you can maximum write x power 0, and this is the term with 0th degree. Okay, so homogeneity means it should be same everywhere. Okay, so here in this case, if you see, this first term and second term have degrees equal to 1, but the third term has a 0 degree, which means ultimately these two these two has degree 1, but the third term has degree 0. So all these don't have the same degree, so it's not homogeneous. Clear? As long as you have a constant in any of the equations, then in linear equations, of course, okay, in any linear equation, if you have a constant, then ultimately that equation is a non-linear equation, non-homogeneous equation actually. Clear? In matrix, we always represent solution of linear equations as vector matrix. Yes. Okay. Did you understand what is a non-homogeneous equation? Of course, all the terms will not have the same degree, which means there is some involvement of constant in the linear equation. Clear? So please type in the chat box. Is this clear to all of you? So please type in the chat box. Is this clear to each and every one of you? Okay. Now, in this case, if you have this non-homogeneous system, then clearly this x has n number of unknowns because there are n by 1. Then you can see for the system, option first point, to have a unique solution, rank of A should be equal to rank of A augmented with B, and this should be equal to n, and n here is clearly number of unknowns. Okay, it's not the equations, because this tells you it has m equations and n unknowns, so this should be equal to n, of course. Okay, so number of unknowns. Clear? Then second, to have infinitely many solutions. Infinitely many solutions, to have infinitely many solutions, rank of A should be equal to rank of A augmented B, undoubtedly, but this is less than n. In both these cases, the system has a solution, maybe single solution or infinitely many solutions, but still this system has a solution, and these two are the cases of consistency. We say system is consistent. System is actually consistent, means it has a solution. Clear? Is there any physical significance of homogeneous and non-homogeneous equations, sir? Of course, why not? See, for example, if you do this equation, let's say mx double dot plus kx or cx dot is equal to kx plus some exciting force, let's say, okay, f of t. Now, if this force is actually a constant value, let's say some 10 newtons or 5 newtons, whatever, then if this is a constant, then all these terms are of linear degree, but this do not have. Okay, so this is a differential equation. And coming to, okay, if you talk the things in simple business, for example, let's say whenever you are solving equations, if you get there are a lot of things, even in aptitude questions you'll get this, right? 5x minus 2y is equal to 7. So let's say, for example, if I ask 5 times of my age minus 2 times of your age, the difference between those two is 7, then you will form this equation. So clearly you'll have a nonlinear equation. Okay, but let's say there are 8 apples or 8 baskets of apples and 9 baskets of oranges, such that total number of apples and total number of oranges are equal, then you'll have equation like this. Okay, it forms a linear equation. It forms a homogeneous equation. Clear? That's all. See, I am telling, this word physical significance is used very you know, very loosely in today's world. Okay, but everything actually physics gives you mathematical equations, simple. Okay, clear? I hope you have understood this. Okay, for example, let's say if I say the statement 5 times my age minus 2 times your age is equal to 7. Okay, then let's say if you take my age as x and your age as y, for example, then you will end up with this equation where there is some non-homogeneous term in this. Okay, but let's say if I tell you there are 9 baskets of apples and each basket has some x apples. Similarly, if there are or 9 baskets of oranges and each basket has y oranges, and total number of apples and total number of oranges are same. If I tell this, then ultimately this is what you'll get. Correct? So it's a non-homogeneous. It's a homogeneous equation. Clear? Because you see there are only 2 terms. Each term has degree 1. That's it. Now let's see. Third. For the system to be inconsistent, for the system to be inconsistent, for the system to be inconsistent, that is no solution, rank of A is not equal to rank of A augmented with B, of course. Okay, so rank of A is not equal to rank of A augmented with B. So these are the 3 important conditions which decides the consistency of the systems actually. So normally in case of 2 by 2 or 3 by 3 you can check manually, but let's say if I give you some 70 by 70, okay, 70 equations with 70 unknowns or 72 equations with 69 unknowns, if I give you things like that, rather than first initially start solving the question, you should check for the consistency of the system. If this is not consistent, then ultimately you should wait and do something to the system so that you'll have a solution. Okay, that's what. Is this clear to all of you till this points? Yes or no? Is this clear to each and every one of you? Please type in the chat box. Okay, just a minute, I'll have some water. Everyone is understanding the things or not? Yes or no? Everyone should type in the chat box, all of you. Now, okay, so let's continue. So let's see, we have one important thing here, linear combination, linear dependency and linearly independent. Okay, but before going for that, I would like to tell you one important thing here. Look, homogeneous system of equations. Homogeneous system of equations. Okay, homogeneous system of equations actually. So let's see, you have this system A m by n, x n by 1 is equal to b n by m by 1, of course, but let's say this b is a 0 vector, this is a null. Okay, so that means b is equal to 0 0 and so on, 0 of size 1 by n whole transpose on 1 by m. Okay, so this is of some size 1 by m whole transpose, so it's basically m by 1 and it's a 0 vector, so the right hand side is completely 0. Then ultimately this becomes a homogeneous system. Okay, now let me tell you one thing, I'll explain you with the case of a 3 by 3, you'll understand. Say m equal to n equal to 3 for example. Okay, so because I just want to show you one important thing, example, say m equal to n equal to 3. Now if you look at the system turns up something like this, a11 x plus a12 y plus a13 z is equal to 0, a21 x plus a22 y plus a23 z is also 0, a31 x plus a32 y plus a33 z, this is also 0 actually. Okay, so let's say you have these 3 equations and ultimately those are homogeneous equations because the right hand side is 0, the coefficient value is 0. Now if you try to convert this into a mathematical system of equations, you can end up with A11, A12, A13, A21, A22, A23, A31, A32 and A33 actually. Okay, so this multiplied with x, y, z is equal to 0, 0, 0. This is what you have. Okay, now clearly A is this matrix, A equal to A11, A12, A13, A21, A22, A23, A31, A32, A33. Okay, so this is the matrix. Then you have A augmented B is equal to this A11, A12, A13, A21, A22, A23 and A31, A32, A33 of course, and also you will add this elements which is 0, 0, 0 of course. Okay, now when you add these elements, first of all this is of size 3 by 4, you know, this is of size 3 by 4 and this is of size 3 by 3. Now if you form 3 by 3 minus for example, okay, so the maximum possible rank could be 3. So let us check the 3 by 3 minus. If you check the 3 by 3 minus, the first thing that will have is determinant of A of course. Okay, this is one 3 by 3 minor because this matrix is also present here, so definitely this could be the first minor. Now if you delete first column, you have A12, A13, A22, A23, A32, A33, then these are zeros. If you delete second column, for example A11, A13, A21, A23, A31, A33, then you have zeros. Okay, then if you delete third column, you have A11, A12, 0, A21, A22, 0, A31, A32, 0. Let's say you have this. Okay, then when you have these things, clearly one thing that you know is these determinants will go to 0 because they all have one complete 0 column, and if you expand the determinant about, so that equal to 0 for augmented matrix. We'll see. Okay, just a minute. So if you see this 3 by 3 minus, if you take this 3 minus will definitely go to 0, which means the rank of this matrix being 3 or not, it depends on this det A, correct? Yes or no? Similarly here, rank of A, if you check, it depends on det A and of course the elements inside. Similarly here, this is 0, so whatever happens here in the calculation of the rank of this matrix, same thing will also happen here because this completely depends on these elements, which is same as this, correct? Can you understand? Rank of A will depend only on the elements of A undoubtedly, and the rank of A augmented B will also exactly depend on the same 9 elements which are here. 2. Will you all agree this? Yes or no? Please type in the chat box. Can you understand this? Rank of A and rank of A augmented B both depend only on the elements of A, correct? There is nothing like this happens something differently and this happens something differently, because both are actually depending on the same elements. So ultimately this rank of A is dependent on rank of A augmented B. So therefore rank of A is always equal to rank of A augmented B in case of homogeneous systems. In case of or for homogeneous systems. Okay, see Thomas, it's very simple. Look, what I'm telling here is this is 3 by 3, all these 3 are zeros, so you have only one 3 by 3 minor which is same as this matrix again. Okay, now let's say for example if this determinant is 0, then a rank of A will not be 3, it is something less. Similarly if det A is 0, then all the 3 by 3 minus are 0, you will again go for 2 by 2. Okay, so what exactly happens here when checking 3 by 3 minus, 2 by 2 minus and all, same thing will also happen here, and the rank of this A and the rank of A augmented B will always be same because they depend on the same set of elements. Here this rank of A depends on this 9 elements. Similarly this rank of this A augmented B also depends only on this 9 elements actually. Clear? Okay, so basically what I want to tell is, in non-homogeneous systems, in homogeneous systems, there is no case where these two are not equal. They are always equal. Okay, that means there is no case such that this system don't have a solution. It tells you that this system always has a solution, maybe unique solution or infinitely many solutions, we don't know, but this rank of A and rank of A augmented B are always equal. That means this system will always have a solution, and clearly, you know, if you put x equal to 0, y equal to 0, z equal to 0, that solution will definitely satisfy this equation, whatever these elements are. Yes? Is it clear to all of you? If you put x equal to 0 and y equal to 0 and z equal to 0, it doesn't matter what are the elements inside A, this equation will always get satisfied. I mean, this system of equations will always get satisfied. 2? Will you all agree? Yes? So, which means it's not like this system never has a solution, this system will always have a solution. Clear? Now, when could be the case where this system has infinitely many solutions? Okay, so first of all, look carefully here. Since rank of A is equal to rank of A augmented B in all cases, this implies homogeneous system is always consistent, is always consistent. Okay, so this is always consistent. Now coming to point 1, okay, so case 1, if rank of A is equal to rank of A augmented B is equal to 3 in this case, okay, because we have taken 3, means this implies determinant of A is not equal to 0, correct? Because if this rank of A has to be 3, then ultimately this determinant should not be equal to 0, of course. Okay, so of course determinant should not be equal to 0. So that means for this to happen, I mean these two are anyhow equal. If these two ranks has to be 3, then determinant of A should not be equal to 0. And whenever these ranks are equal and it's also equal to number of unknowns, this 3 is the number of unknowns in these examples, whatever we have taken, number of unknowns, then the system has unique solution, has a unique solution. Okay, then the system has got a unique solution, of course. Now when the system has got a unique solution, now what is that unique solution? That means this particular system has only and only one solution, and that solution is, and the solution is x, y, z is equal to 0, 0, 0. That's it. Okay, this is the only solution that the system will have, and this solution is always a solution independent of A. That's why it is called, this solution is called trivial solution. Okay, so this is called trivial solution. Trivial solution. That means it never depends upon the elements of the A, it's always 0. Clear? So in the augmented matrix it has one whole column 0. So does it mean the determinant is 0? See, first of all, augmented matrix is need not be a square matrix. Okay, got it? Like for example, you see here, this is a 3/4 matrix. For a 3/4 matrix, can you calculate determinant? Alex, please type in the chat box, for a 3/4, can you calculate a determinant? Please type in the chat box, can you calculate determinant for a 3/4 matrix? Yes or no? No, correct? So if you cannot calculate, then what you'll do, you'll go for the maximum possible minus actually. Okay, that's why since this is a 3/4, you cannot calculate a 4/4 determinant, we come for the 3/3 minus. Clear? And when you come for 3/3 minus, it's not like all are 0, there can be some det A where which is non-zero. Okay, so because determinant of A means if you take these 3 columns as one of the minor, this 3 columns determinant is same as determinant of A. So that's why this being 0 or not, it depends upon det A, which is nothing but these elements. Clear? Now did you understand? Got clarity why that's I am not taking 0 directly? Because it's not 0 directly always. It depends upon the determinant of A actually. Got it? Okay, nice. Now let's see. This is called trivial solution, and it's called trivial. Trivial means by default. Okay, by default, this is always a solution of the given equations. Now let's see here. Case 2. Case 2. For the homogeneous system, or for a homogeneous system to have a non-trivial solution, that means along with having one solution, see, basically it can have, see, the system is consistent anyhow. We have found out rank of A is always equal to rank of A augmented B. Now the possibilities are two possibilities. Either it should have unique solution or it should have infinitely many solutions, of course. Okay, now whenever you have one solution, we have found out what's happening here. Okay, if it has one solution, then ultimately this number should be equal to 3. That means that not equal to 0. We found out what is that solution. Now if you want to have infinitely many solutions, that means along by having this trivial solution, the system has some other non-trivial solutions also, correct? So if the system has to have a non-trivial solution, then rank of A should be equal to rank of A augmented B should be less than n. If this has to be less than n, okay, here in this case you write 3, this has to be less than 3. If this has to go less than 3, that means this 3 by 3 minor which is there should also be 0, correct? So this implies determinant of the coefficient matrix has to be 0, of course. Okay, so this implies determinant of A should be 0. That means in a homogeneous system, if coefficient matrix determinant is 0, then we have a non-trivial solution. If that is non-zero, we have only a trivial solution. Clear? Is this clear to all of you? Yes or no? Please type in the chat box. Is this clear to each and every one of you? Yes, these points are very important. Okay, that's why. See, basically what I'm telling, if this rank of A has to be less than 3, when rank of A is less than 3, if this determinant is actually 0, okay, then only we'll go for 2 by 2s. So this determinant is actually 0 if your rank has to be less than 3. That's what we have seen. So if this has to have a non-trivial solution, determinant of this coefficient matrix should be definitely 0. Clear? Based on this, we have some questions in GATE, not some, many questions in GATE actually. Okay, so now let us go for some questions, some previous year GATE questions which could help our understanding better. So let's see, let us solve this question. It's a 2 by 2. It's a 2 by 2. So solve. I'm giving some integer type. Okay, integer type, and then integer type, maybe some 90 seconds. Okay, 90 is more. Okay, fine, you take, no issue, just solve it. Consider a matrix. This is a matrix and vector x1 x2. The number of distinct real values of k for which the system Ax is equal to 0. This is a homogeneous system, has infinitely many solutions, is dash. How many values of k you have, so that it has two distinct, basically infinitely many solutions. Okay, so how many distinct values of k can give you infinitely many solutions for that system? So could you please share your contact? I'll have interview in IISc, so I want to connect with you. You can just message in that telegram Amrit. Okay, I'll respond. Okay, maybe not immediately, but I think just give me some some time, because there are many other messages as well, so I'll definitely respond to you. Clear? Okay, since IISc interviews are going on, I'll respond immediately after the class. Okay, maybe you might have messaged, but I might not have seen, but it's okay. I'll respond immediately after the class if it's in the telegram group. Okay, Ashwini is telling 1, Sagnika 2. Okay, good. Then I'll respond, Amrit. No issues. Okay. See, again I'm mentioning, in this batch I'm solving only questions which are easy to moderate. Okay, I'm not going for very tough questions as of now, because that we are going to store for the practice sessions. Clear? Fine. Okay, now let's see, if you just now we have seen the system is k, 2k, k square minus k, k square, x1, x2, 0, 0 clearly, okay, and this is a homogeneous system. A homogeneous system, okay. Now if this is a homogeneous system, clearly for the system to have non-trivial solution or infinitely many solutions, to have infinitely many solutions, the concept that you have learnt is determinant of the coefficient matrix, which is k, 2k, k square minus k, k square. This determinant should be 0 actually, okay. Now if that determinant is 0, if you simplify this, k into k square, k cube minus 2k times k square minus k is equal to 0, of course, okay. So if you simplify this, k cube minus 2k cube, which is minus k cube, then minus 2k minus k, which is plus 2k square, is equal to 0. So k square times, if you take common, then 2 minus k is equal to 0, of course, okay. So k equal to 0, comma k equal to 2. Now you can check one important thing. First of all, if this k equal to 0, here you can feel that there are two values, okay, but if you put k equal to 0, first of all, this system itself will not exist, yes or no? They are telling you this system has infinitely many solutions, okay, but if you consider this k equal to 0, then ultimately this, first of all, this system itself will not exist, correct, because you put all elements 0, 0 equal to 0, it's an identity, correct, it's not a system anymore, it's an identity, right, yes or no? If you put k equal to 0, then ultimately this matrix will be a null matrix, okay, and null matrix into anything will be 0, of course, the system itself will not exist actually in such case. 2, yes or no, correct? Are you understanding things or not? If you put k equal to 0, then definitely this matrix will be 0, okay, null, clear? Then there is no system to deal with. So there is only this value which survives or makes this system has infinitely many solutions, clear? So we have only one distinct value. Got it? I know why you have type 2 is because you got 0 comma 2 as two solutions, but physically when you put k equal to 0, it goes up, okay. So these are the points you have to think, okay. Whenever I am giving questions, it's like people felt that it's a 2 by 2 matrix, so very easy, equate the that to 0 and write the answer, but the system will not exist actually in this case when you put k equal to 0. So physically k equal to 1 is the only thing which is possible for you. Got it? So 1 is the correct answer. I think Ashwini has typed 1. Yeah, Ashwini Kumar Baiswal. Nice. Okay. Now let's go to the next question quickly. See, when you are solving all these questions, you are trying to learn all the pitfalls, okay, where basically you can commit mistakes and all, you are trying to learn. So please learn these things, okay. It's not like I know you can calculate 2 by 2 determinant and tell me what are the values of k, but once you get the values of k, what are the things you are going to do, okay. Now let's see, let us go to this question. Consider the following linear system. The x plus 2y minus 3z is equal to a, 2x plus 3y plus 3z is equal to b, and 5x plus 9y minus 6z is equal to c. The system is consistent if a, b and c satisfy the equation which are one of the following equations, okay. So again I'm giving you some time, it's a 3 by 3, it's a lengthy question, obviously. I'll give you some timeless poll is what I'll click, but I'll give you time of maybe 3 minutes to solve. Let's bring up the timer, okay. So I'm giving 3 minutes, fine. By the time this ends, I'll end this poll also. Enter, okay, 3 minutes to solve this, quick. It's a linear system and you want to have a consistent system, okay, then what should happen? Alex, I have it out. Yeah, please see, if you have doubt you can ask directly, okay, you need not take permission or something, you can just ask. If you have doubt, please ask me. Ashwini Kumar Baiswal, B, very fast, how come? So even when these conditions such as 2 rows or columns are same or entire rows. So even when these conditions such as 2 rows or 2 columns are same or one entire row column is 0, then the rows are proportional are not meant, but still they can be that equal to 0. See, I'm telling you now, if you have a determinant, okay, you can calculate determinant. You can calculate determinants only for square matrices, right? You cannot calculate for non-square or rectangular matrices. So all those properties what I have told you will be valid if you have a square matrix. Clear? Minor is something different from determinants. Okay, so please take care of this. Minus you can write even for a non-square matrix, but determinant you cannot calculate for a non-square matrix. Okay. Fine. Then what do you mean by they are not meant? They meant actually, right? In case of a square matrix, if any one of these things happen, then we have checked and we have got determinant is equal to 0. Correct? What do you mean by are not meant? Actually, I did not get that point. Last 30 seconds. Do it quick. B is coming. Yeah, I think B should come. Correct. Eight, 7, 6, 5, 4, 3, 2, 1. Okay. So I'm closing the poll, of course. Then let's hide up the poll somewhere and let's stop the poll also. Fine. Okay. Now let's see. We have stopped the poll. First of all, like this need not be followed for det to be 0. Yes. See, I'm telling you, whenever you have all these things, then determinant is 0 too. But for det to be 0, these things need not mandatorily happen. Okay. See, I have never told if det is 0, then rows are proportional. If det is 0, then one column is 0. I have never told this. If one column is 0, then det is 0. That's what I have told. Okay. Converse need, if determinant has to be 0, then you need not have these things in the matrix. Got it? Converse need not be true always. Okay. Like for example, Monday to Friday, it's like 5 days, but Friday to Monday, it's only 3 days. Okay. So things like that. Okay. Now let's see in this case. I just tell you one thing. You call this equation 1, you call this equation 2, and you call this equation 3, for example. And let's say you have x, y, z. There are some particular values of x, y, z which could satisfy these equations. Okay, because it has, the system is consistent. Okay, so the system is actually consistent. The system is consistent. So that tells you ultimately A, B, and C is what you have. Okay, and there is some values of x, y, z which satisfies these equations. Now, for example, if you try to eliminate these equations, okay, if you try to eliminate the left hand side, if you calculate 3 times of 1 plus B minus C, if you do this, okay, so if you do these things, 3A plus B minus C, or 3A plus 2, 3 into 1 plus 2 minus 3, if you do this, we'll get 3 into x plus 2x, 5x, 5x minus 5x, 0, plus 3 into 2y, 6y, 6y plus 3y, 9y, 9y minus 9y is 0, minus 3z. So 3 into minus 3z, minus 9z plus 3z, minus 6z, minus 6z minus of minus 6z is again 0. This should be equal to 3a plus b minus c. Okay, this is what you get. This is a slight trick so that if you can somehow eliminate this x, y, z, then ultimately you will get the things in terms of coefficients. But anyway, this trick need not strike always in the examination hall. So what we'll do is, see here, we consider the augmented matrix, the general way of solving. Consider A augmented B, of course. Okay, so A augmented B is equal to 1, 2, minus 3 A. Okay, then 2, 3, 3 B. Then you have 5, 9, minus 6, C. Okay, so this is what you got. Now let us try to convert this into echelon form. We'll see what happens. R2 changes to R2 minus 2R1. R3 changes to R3 minus 5R1. Okay, so this is what you have, R3 minus 5R1. Now let's check it up. A augmented B turns up like, first row doesn't change, the same elements you have, 1, 2, minus 3, A of course. Then second row, 2 minus 1 into 2 minus 2 into 1, 0, 3 minus 2 into 2, minus 1. Okay, so because R2 changes to R2 minus 2R1, so 3 minus 2 times of 2 is minus 1 actually. 3 minus of 2 into minus 3, so this is 9 of course, because 3 plus 6 roughly. Then B minus 2A, this is what you will get. Okay, this is B minus 2A. Now coming to C, you have 5 minus 5 into 1, 0, 9 minus 5 into 2, this is minus 1 of course. Then minus 6 minus 5 into minus 3, so minus 6 plus 15 is 9. Okay, then after this value is C minus 3A is what you get. Okay, C minus 3A. Now let us get one thing. Again, this is not in echelon form, so you want to make this element 0. If you want to make this element 0, then you can apply R3 changes to R3 minus R2. If you apply this transformation, you can find one important thing actually. This is the main crux in this problem. Look, the first and second rows, they remain as it is. You have 1, 2, minus 3, A, 0, minus 1, 9, A, B minus 2A, B minus 2A, 0. Now if you perform this transformation, R3 minus R2, 0 minus 0, 0, minus 1, minus of minus 1, 0, 9 minus 9, 0, then C minus 3A plus B minus 2A of course. Okay, so C minus 3A, C minus 3A minus B minus 2A, B minus 2A. This would be the matrix of course. Okay, now tell me one thing, C 5A sir, C minus 5A, where it is C minus 5A, yeah correct, 2, this is C minus 5A, C minus 5A, correct. Okay, so that means C minus 5A, this is what you get. Now try to understand something guys. If I have converted, let's say for example, if I want to calculate a rank of A initially, okay, I have this matrix A, means basically this part is actually A. If I want to calculate a rank of A, and I can calculate rank of A by converting A to row echelon form also, correct? If I convert A to row echelon form, I would have got this matrix, yes or no, correct? Means if you see, A would have been something like, if I have converted A to row echelon form, I would have got 1, 2, minus 3, 0, minus 1, 9, and 0, 0, 0 actually. This is what I would have got. 2, yes or no? If I want to calculate rank of A, and if for calculating rank, if I have converted A to row echelon form, I would have got that matrix, which is exactly from here, from this part. Yes, because the same transformations I'll apply, and that's the matrix I would have got actually, which is on the corner. Yeah, type in the chat box, yes or no? This is the matrix I would have got if I have converted A to row echelon form, because this is the same thing actually. Now can anyone tell me what is rank of A? What is rank of A actually? Can anyone tell me what is rank of A by looking at that row echelon form? By looking at that row echelon form, can anyone tell me what is rank of A value? 2. Now if this system has to be consistent, for the system to be consistent, what you can have is rank of A should be equal to rank of A augmented B, and you have found this rank of A is equal to 2 actually. Okay, so this should be 2 because you clearly found rank of A is 2. Now if rank of A is 2 and if this system has to be consistent system, then this rank of A augmented B should also be 2, correct? If rank of A augmented B has to be 2, the number of non-zero rows in row echelon form of A augmented B should be equal to 2. Yes, will you all agree this logic? Yes or no? Anita, Vasishta, Maunika, Sagnika, Prakasam, Vivek, Aya, everyone, correct? If this has to happen, then ultimately in this augmented in this basically echelon form, row echelon form, I should have only 2 non-zero rows. If I should have only 2 non-zero rows here, then definitely this element has to be 0. This has to be 0 then. Okay, so therefore C minus 5A minus B minus 2A is equal to 0. This implies C minus B minus 5A minus of minus plus, so minus 3A is equal to 0. This tells you 3A plus B minus C is equal to 0 actually. Okay, this is how practically you can calculate. See, it took some time because I made you to understand things. Okay, but if you just calculate, it takes you hardly 2 minutes. Okay, yes, can you understand this? Thank you for so much love. But I'm just telling you one thing, guys. Look, in order to get till this point, you have to just apply 2 steps of transformations. Okay, like firstly you'll form this matrix, you apply one set of transformations, you'll come here, then apply your second set, you'll come here, then whatever I have written on board from this part to this part, that's the common understanding of this system of equations. So if you know this, immediately you'll make this element to 0, then this is the equation that you'll get. Okay, so therefore that also gives you B as the correct answer actually. Okay, so B will be the correct answer obviously in this case. So if you check, B is the correct answer. Oh, 100%, many of you. Ashwini, Aya, Labby 5805, good. Okay, yeah, no issue, but I hope you all have understood this. Okay, so the main thing is, in this, whatever you are doing for A augmented B, just if you pick the first 3 columns, same will be A. Okay, if for converting to echelon form. So chalo, let's go to the next question once. This is a very nice question. I just want you to try. This is a homework question, okay, for you today. Homework question. So this is a homework question. So can we do simply that of 3 by 3 minus of augmented matrix? You can do, no issues. Okay, but if you do, then see, if you do, one thing that you should do is you take any 3 by 3 involving ABC and you equate to 0, then you will get the same answer. Then we get the answer, no? Yes, you will get. Okay, the main thing is I just want to show you this purpose. One thing you can also do is, first you should calculate that A. First you calculate that A. Okay, alternative way, I am just teaching you alternative method. First you calculate that A. Okay, if you calculate that A, ultimately you will get 0. Okay, you can try, you can just calculate. Okay, so 1 2 minus 3, then after 2 3 3, 5 9 minus 6. Okay, so this is what you get. So if you calculate this determinant, you'll get 0. You can try. Okay, you can try, you'll get 0. Now once you get 0, see, this calculation of determinant takes some time. Okay, first of all, then calculate this determinant. By the time you know this is 0, then determinant of A equal to 0. This implies rank of A is not equal to 3. Okay, this is what you'll come to know here. At this stage, you will come to know this is not equal to 3. If this is not equal to 3, then ultimately you will come to know this implies for system to be consistent, for system to be consistent, rank of A should be equal to rank of A augmented B. This implies rank of A augmented B should also be not equal to 3. This is what you will understand. It should be less than 3. Okay. Now if this is less than 3, then ultimately this implies all 3 by 3 minus of A augmented B has to be 0. This is what you'll also understand. Okay, this is also what you'll understand. Now if all 3 by 3 minus of A augmented B has to be 0, then definitely you choose any 3 by 3 that should be 0. Okay, so you pick any one random such that that involves ABC. Okay, because look, you take, see, basically you can form 4 3 by 3 minors. Okay, so out of 4 3 by 3 minors, you choose any one minor which is involving ABC. Okay, because if you don't involve ABC, again you will get determinant of A only, that you have already calculated. So let's say, for example, if I'm skipping the first column, if I skip first column, see this is the matrix. If I skip the first column, this 3 by 3 minor should also be 0, or if I skip the second column, the 3 by 3 should also be 0. If I skip the third column, then also it should be 0. So let me skip the third column. If I skip the third column, I have 1 2 5 is what you'll get. 1 2 5 2 3 9 2 3 9. I am skipping the third column. A B C. This determinant should also give me 0, of course. Okay, in fact any 3 by 3 determinant I take, that should be 0, because this rank cannot be 3, it should be less than 3. So if you simplify this, you will get 1 into 3C minus 9B minus 2 into 2C minus 5B plus A into 18 minus 15 is equal to 0. If you simplify this, you get 3C minus 4C, which is minus C, minus 9B plus 10B, so plus B plus 3A is equal to 0. This gives you 3A plus B minus C is equal to 0 actually. Okay, that's how you can still get the condition. See, there are plenty of ways to work out. Okay, but this method, see, luckily here it's a 3 by 3 matrix. Okay, but let's say if I give you 4 by 4 and the rank is 2, then after checking 4 by 4, you'll get that 4 is equal to 0. Then you should start checking for 3 by 3 also, then again 2 by 2. So this increases the number of calculations that is involved. Okay, Vasishta, got it? Otherwise I would have done this also, because calculating determinants is always easy, but this method has got a limitation. If the size of the matrix is huge, then this method will take a lot of time, because you physically has to inspect all the 4 by 4s, 3 by 3s, and then come to 2 by 2s. Okay, but this will definitely have a classical set of procedure which gives you solution sometime. Clear to all of you? Yes or no? We only do for 3 by 3 matrices. In gate level, generally there came situations where 4 equations on 3 unknowns, or 3 equations with 4 unknowns, things like that has come up. So better to follow one classical procedure. Okay, see, you can do this, nobody can stop you, you can do the methods, but at the same time they should be optimal. Okay, because we have some time limit also in the exam, so that's what. Fine, I hope all these things are clear. Okay, so let me quickly give you some idea on eigenvalues and eigenvectors. Of course, anyway, I think I cannot finish today, but I'll just a minute, guys. So where is this? Okay, we are solving some questions. Fine. So let's go to eigenvalues and eigenvectors, because I want to teach you one more concept in system of equations, but that involves talking about linear combinations, linearly dependent and linearly independent, which we'll deal in the tomorrow's class. Okay, so in tomorrow's class we'll deal with vector spaces, subspaces, then linear combinations, basically linear and nonlinear equations. Maybe I think I need one more lecture on Monday also. Normally the plan on Monday is to talk about this single variable calculus, to start with single variable calculus, but I think since I promised that I'll cover all this data science syllabus and also basically data science syllabus also, so I'll need one more lecture. So on Monday also we'll discuss only linear algebra. Okay, because I have to talk about partition matrices, which I think I cannot do it tomorrow because the time is short, because I have to go deep into eigenvalues and eigenvectors, and then go for eigenvalues and eigenvectors, then we'll go for diagonalization of matrices. Okay, and after diagonalization we'll start looking at linear combinations. Then we will, I think this will take tomorrow's lecture. Then on Monday we'll talk a bit of LU decomposition or Gauss elimination. Okay, we have some methods to solve linear systems, we'll see these methods, and also we'll talk some properties of partition matrices actually. Okay, partition, and also this what do you say, partition matrices, and also this power matrices. Okay, we'll talk about that. Clear? No class for tomorrow and Sunday. Sunday there is no class, tomorrow there is class. Okay, tomorrow we have class. I told you this batch is from Monday to Saturday. Okay, I can take class on Sunday, but actually, to be honest, if it's not like only I come and take the class, there is so many backend team which is working, but for them it's holiday, so let them have some entertainment. Okay, it's like I can teach for 2 hours and you can listen for 2 hours, but people who are in the background should also work for 2 hours. Okay, in fact more than 2 hours. So we should never go into the personal space of people, correct? So that's why. Okay, cool, good enough. Then let's see what are eigenvalues and eigenvectors. So first of all, how do you calculate eigenvectors? Okay, so let's see eigenvectors. Eigenvector eigenvector. So let's see a vector x is said to be an eigenvector of a matrix A, is said to be an eigenvector of matrix A if is said to be an eigenvector of matrix A if there exists a scalar lambda in bracket. Lambda can be real or complex. It can be a complex number. Few times, especially in skew symmetrics and all, we'll find complex numbers. Okay, a scalar lambda such that here a small correction, guys, please make this correction, a non-zero vector. Okay, non-zero vector, please make this, it's non-zero. Okay, so a non-zero vector x, clear? A non-zero vector x is said to be an eigenvector of a matrix capital A if there exists a scalar lambda. Scalar is some physical constant maybe, so lambda can be real or complex such that ax is equal to lambda x, which means physically, that is physically when A is operated on x, it just changes the length. It just changes length of x, but not its direction. Because you can see, whenever you have a vector x bar, and if you are multiplying any vector by a number, okay, it's a scalar. Okay, so if lambda is just a scalar, then ultimately it will just change the length. Okay, so it will not actually perform a rotation of the vector actually. So clearly this lambda into x will be in the same direction as that of x. See, for example, guys, look, let's say if you have a vector, so xy, let's say if I am talking in xy coordinates, x y, okay, and then you see, let's say this is a vector x, for example, this is a vector x bar. Now if this is vector x bar, now if I keep changing the length, the vector will always lie along the same line of action, yes or no? For example, if this is the line of, let's say this is vector, some line of the vector, then this vector, if I am not changing its rotation, if I am changing only magnitude, then definitely maybe the sense gets reversed depending upon lambda can be negative, but this always lie along this line. It never get to a different orientation actually. Okay, so that's what we have. And why I have written non-zero is, if this is 0, then this equation is always satisfied, yes or no? It's like the trivial solution case, yes or no? If this x is 0, then this matrix multiplied with x 0 0 0 is equal to lambda into 0. See, for any value of lambda and any given matrix A, this equation is always satisfied, but it's not like that. Okay, whenever we give a particular matrix, we want to know the vectors in such a way that when this matrix is operated on that vectors, only length changes but not orientation. Okay, so that's what we have. Now tell me one thing, we have Ax is equal to lambda x. This can be written as ax is equal to lambda times I into x, correct? Because this x can be replaced with I into x, identity into x always gives you x. If you shift this form, a minus lambda I operating on x is equal to 0. This is what we have, okay? So a minus lambda I operating on x has to be 0. Now this is a system of linear equations, yes or no, correct? This is some matrix, let's say B for example. If this matrix is B, say let a minus lambda I is equal to B, this implies B times x is equal to a null matrix. This system is a homogeneous system, yes or no? Will you all agree? This system is a homogeneous system now, because a minus lambda is some matrix, okay? So because matrix minus some scalar into identity matrix will again definitely give you some matrix, okay? So this is some matrix B, and this is x, the vector which we are talking, which has some unknowns x1, x2, x3 and so on like that. So B into x is equal to 0. So this is a homogeneous system of equations, correct? So this is a homogeneous system of equations. Homogeneous system of equations. Now if this is homogeneous system of equations and this x is non-zero, which means this system of equations has a non-trivial solution, yes or no, correct? Because we have defined x to be non-zero initially, that means this x is non-zero. If this x has to be non-zero, that means this system of equations has a solution for x which is non-zero, which means this homogeneous system has got a non-trivial solution, yes or no? True? Can you understand this statements? This homogeneous system has a non-trivial solution. That's what I'm telling. Yes? Can you all agree? Yes or no? Will you all agree or not? Please type in the chat box. This is a homogeneous system with a non-trivial solution, correct? So the system Bx is equal to 0 is a homogeneous system with x not equal to 0. With x not equal to 0, of course. If x is not equal to 0, then for this to happen, we have checked it. Look, you can see we have seen here. If this is a homogeneous system with a non-trivial solution, definitely the determinant of the coefficient matrix, if my system is Ax is equal to 0, for example, you can see we have started with this system Ax is equal to 0. If this system has to have a non-trivial solution, we found this determinant. Of course, in this 3/3 case, we have seen the determinant is actually 0. Okay, so for a square system, if this determinant has to be 0, that means determinant of B has to be 0. Of course, if determinant of B has to be 0, what is B? B is nothing but this a minus lambda I is what we have taken. So determinant of a minus this lambda I has to be 0. Of course, this is the condition for that system to have a non-zero x. That means for a given matrix to have eigenvectors, the values of lambda are calculated using this equation. Clear? And this equation is called characteristic equation. Characteristic equation of the matrix. Generally, people tell you calculate that of a minus lambda equal to 0 to find eigenvalues. But why you should calculate that of a minus lambda equal to 0? Why you are very much interested in that of a minus lambda I? Because the reason is you are interested actually not in finding lambdas, but actually you are interested in finding those set of vectors which do not change their orientation when you apply a particular matrix. And to calculate such vectors where rotation never takes place, it's only the change in length. So to identify such vectors, you should calculate this det of a minus lambda equal to 0, because the system should have some x existing. That's what. Clear? Is this clear to all of you? Yes or no? Please type in the chat box. Okay. So this is the equation with which you will calculate actually the eigen values. Okay, and I hope this you all know. We have seen it many times. Okay, so anyway, the time is short today. Only we have roughly 10 minutes. I could not do much beyond this. So we'll stop this lecture here as of now. Okay, so anyway, I'll just give you one important thing which you can. I'll give you one homework question which you can do. This is one homework question, and since you can try this also. Okay, a value of x for which the matrix, see this is the matrix x for which you have 0 as an eigenvalue. This is also homework question. Okay, so these two questions you try as homework, because now you know how to find eigenvalues. So if this matrix has one eigenvalue 0, then what is the value of this x? That's what. Okay, so do this question. So these two questions I would like to give homework. So today we have majorly talked about system of equations, and also we have worked on the concept of this eigenvectors I have introduced. Basically you will have a system which is this, so a minus lambda I of x is equal to 0. This is a non-homogeneous system. Sorry, this is a homogeneous system. So for non-zero x to exist, that of a minus lambda I has to be 0. This is what we have seen. Okay, so in tomorrow's class we will start with this equation. Actually we have seen why that of a minus lambda I has to be 0. We have understood this. Now using this equation we'll calculate lambdas and we'll find the corresponding eigenvectors actually. Okay, and we'll discuss a lot of properties of eigenvalues and eigenvectors. Every year in any question paper, without a question of eigenvalues and eigenvectors there will be no question paper. Okay, I'm telling you, because if you look at the past analysis, the main questions that comes from linear algebra are either from system of equations, eigenvalues, or from the matrix algebra what I have taught you. Okay, determinants very rarely they ask here and there, because ultimately to calculate this eigenvalues you need to use determinants. Okay, so that's why they generally ask you this. Clear? So I've given you two homework questions. Okay, I have some more questions, but anyway we can put it later. This question also you can try. This is also a homework question. Don't get afraid by looking at the terminology. Study the question. It's a very simple question. Okay, so these are the three questions. Fine then. Okay, so we'll again continue at 7 p.m. tomorrow. So Monday to Saturday is what we have the classes. So tomorrow also we have a class at 7 p.m. So we will start eigenvalues and eigenvectors in that. Of course we have started, but we'll see how to calculate them. Okay, and we'll see most important concept of diagonalization, how diagonalization can actually help you. So we'll look at these important concepts of diagonalization. Okay, then if time permits I'll also teach LU decomposition in tomorrow's class. So we'll basically see these kind of things. Okay, so thank you all. We'll meet tomorrow again at 7 p.m. and we will work out a lot of things. Are you all understanding things? Okay, did you all understand the system of equations, each and everything in a good way? Today's class was really helpful, not yesterday's. Yesterday's class was useless. I'm just kidding. I hope I can get thanks for your feedback. Okay, but if you feel that something has to be changed so that this class could be done much better, you can always feel free to share here. I'll try to implement that. Okay, so that all of you get benefited. Fine. Okay, so thank you all. Then we'll meet tomorrow at 7 p.m. Okay, fine then. Take care. Bye.